All right, so if you know him, you are very well familiar that he can be excitable. If you don't know him, you will find out very soon. And when Luke asked me to introduce him, I could only think of one analogy kind of at the last minute, and I need to use the overhead projector for this. While most of us can become excited by a thing such as that, with Nicola, you'll find out very soon in his talk that it doesn't take that for him to be excited about something. That will be perfectly sufficient. So anyway, without further ado, he's going to talk today about the rock physics of geofluids, and I'll get out of the way.
Thank you very much, Kyle. Thank you very much. Thank you for the opportunity of presenting. Thank you for the introduction. Really happy to be here and to show some of the research that's been done in the last couple of years, I would say, in our laboratory upstairs, which is called the Rock Deformation Laboratory, where we typically torture rocks. So if you hear them screaming, these are rocks screaming because we are torturing them. And today I'm going to talk about the rock physics of geofluids, which looks like an oxymoron, but it's not. The first thing I would like to say is that no matter what will happen in the future energy landscape, we will probably have to deal with the subsurface. Geofluids, like oil and gas, have been clearly our resources in the last 120 years. But in the future, we will probably have to deal with the subsurface because we probably have to inject and sequester CO2 in the subsurface. We probably have to store hydrogen. We probably want to start seriously talking about geothermal and all those things. They need the expertise of geoscientists and geophysicists. Just a very recent paper shows, for example, that now we are after the natural generation of hydrogen in the subsurface. It looks like that in origins, in areas where we have, for example, ultramafic rocks, we generate hydrogen naturally, and that would be a great thing because hydrogen is for sure a fuel. Everything we know about everything, or a lot, here there are a lot of geologists, a lot of what we know of the subsurface comes from geophysics. And seismic methods are for sure the method that we've been using, for example, to create the model of the subsurface, which is clearly much more boring than what Jules Verne had in mind 150 years ago. So yes, geophysicists sometimes are very boring people, you know. It would have been much more fun to have dinosaurs in the subsurface with big mushrooms and so on and so forth. But the fact that we can analyze these wiggles, which are seismic traces, we, for example, look at the propagation of an earthquake. We record the propagation of the earthquake around our planet. These are stations. And by looking at the analysis of these wiggles, these seismic traces, we can reconstruct what is beneath our feet. I want to remind you that our planet is roughly 6,300 kilometers radius, and we have been drilling. So what we have been really looking at is up to 10 kilometers maybe, right? There are some rocks which are exhumed that probably went down maybe 40, 50, maybe 100 kilometers, like xenoliths in the some parts which come from the center, but they are extremely small samples. So geophysics is extremely important. And rock physics, and I want to introduce a bit the field that I work on, comes really to the point of studying the physical properties of the rocks and how the microstructure inside the rock is going to influence the properties, because the properties eventually are going to influence those propagation of the waves. And when it comes down, for example, to geothermal, or where to store hydrogen, where to sequester CO2, well, we need to know where to do that. And to know where to do that, we need to know the subsurface, and how the subsurface will eventually react as we inject those fluids. For example, are we going to generate earthquakes by injecting those fluids? Are we going to generate earthquakes by implementing geothermal, for example? So rock physics kind of take care of the lab experiment and analysis and also a bit of modeling theory in order to feed those models, right? Those numerical experiments that eventually will predict what are the the reaction happening in the subsurface and how we can interpret those seismic traces that we have seen before. Rock physics is also material science with humor, according to Professor Gary Markov from Stanford, and I agree with that, right? Okay, so the first part of the talk, I will talk about how we can monitor the injection of gas in the subsurface, and in particular we talk about hydrogen. So this is a map of the US with the Gulf of America down there, right? Gulf of Mexico. The Gulf of Mexico down here, right? And we have all these stars are the major depleted reservoirs, which are typically in sandstones. And those would become eventually extremely valuable to, for example, store hydrogen. For example, the depleted reservoir of Tomball, which is north of Houston, could store 18 terawatt hour of energy in hydrogen. If we inject hydrogen down there at the same condition that methane was down there in the last million of years, we could store 18 terawatt hour of energy, and that's a big number. So the idea is that we have a reservoir, we typically have a cap rock, and then we inject this fluid, which is hydrogen, in the subsurface, and we typically have a cushion gas, which is CO2, for example, and we typically inject inside a reservoir, which can be also an aquifer in case. And the idea is that the production of hydrogen and the injection of hydrogen will eventually change those waves that we have seen before. And now the question is, how does the injection of hydrogen changes those waves as you create, for example, an heterogeneous saturation in the subsurface? The hydrogen goes in the pores, push out the water or the fluid which is in there, start dissolving the water, creates an heterogeneous saturation, which means that it's not able to push out all the water, so you have water and gas now. What is the effect on the elastic properties of the rock, eventually, of that hydrogen, okay? And the question is exactly how those wiggles, those seismic traces, changes as we inject or recover the hydrogen. And here are some papers about hydrogen and how the small-scale rock heterogeneity will change, right? The properties of the rock, right? And an idea is that you do have a heterogeneous saturation. And heterogeneous saturation can, for example, spark attenuation, and I'll go to attenuation later. Attenuation is nothing more than how much energy is absorbed by the material as the seismic wave travels through. I have an animation after. Due to the fact that you do have wave-induced fluid flow, the fact that the seismic wave traveling the subsurface is going to slash around the fluids, and then there is interaction between the gas and the liquid, and that interaction is going to steal energy from the seismic wave, okay? So those are examples of heterogeneous saturation in the subsurface. And in particular, when the quantity of gas is extremely small, you can really create bubbles. You can create bubbles which stays inside in the pores. This is a Fontainebleau sandstone. And you can see here fairly clearly in this CT scan, which is nothing more than the CAT scan for rocks, right? A bubble here, a bubble here. And when you go to volcanic rocks, bubbles are extremely important and are present, and they are also typically the onset of eruptions. So bubbles exist in the subsurface. The model that we can put forward is to have a lot of liquid, the blue, and then somewhere, sometimes you do have a bubble in a pore. And those bubbles are clearly the size of the pores, which are in the order of tens of micrometers. So where does this idea of bubbles in subsurface used, right? I mean, I wrote a paper with some collaborators a few years ago before coming here. We fit some experimental result in which we thought we had bubbles in a sandstone, and I still think we did. And we were able to fit these curves, which they show you how stiff is the rock and how much is the attenuation of the rock. Again, I will go to attenuation in a couple of slides. And using a model that describes how the bubble deforms due to a seismic wave, we were able to fit this data. This came from an idea of a paper from 2006 in which they studied the attenuation in gas charged magma. And lately, there have been some very interesting, in 2021, Lakowski and others wrote a paper about the mantle, or better, the asthenosphere. What happens when you have two phases, right? And one is partially molten phases. What happens when a seismic wave strikes partially molten rock, right? You're going to change the thermodynamic equilibrium between the melt and the solid. And the fact that you are going to change the pressure will move part of the melt into solid or vice versa, and that steals energy, okay? So that's all about the idea that as a seismic wave passes through the subsurface, change the pressure of the fluid, and the pressure controls the thermodynamic equilibrium between the liquid and the gas, or the solid and the liquid in the case of the paper from 2021. Is it really attenuation useful? I think it's very useful. Is it very used? It could be used more. We could use attenuation more to understand better how those seismic monitoring and those seismic images are done. But I want to give you a couple of examples. ZOO in 2018 shows that if you monitor the Frio injection test site, right? If you look at attenuation rather than to look at velocity, you get a much better picture of where is the CO2 plume that has been injected in the subsurface, okay? And at the same time, in 2013, many of you probably remember, in St. Gallen in Switzerland, a geothermal site sparked an earthquake, a 3.5 ML earthquake, which in Switzerland is a big deal, apparently. Our chair is from Switzerland. So it is a big deal because it was the city center, I think, right? And people are not used there to earthquakes. So, and what happened is that they shut down the project. They lost a lot of $1 million probably, or Swiss francs. And the point is that after that, they look at the seismic data, and they found out that there was the clear evidence of presence of gas in the subsurface, and the attenuation was really sparking up as those bubbles probably were forming inside the rock. So we should really start to use it. And it comes down to attenuation. It's really about how much your wave, as it travels away from the point of where it is formed, right, it fades away. You see, in a media where attenuation is fundamentally zero, or the quality factor is infinite, the wave keeps traveling. The unique wave, it doesn't lose the energy. It loses the energy density because you are spreading that energy on a bigger and bigger volume, but you're not really losing energy intrinsically. Okay, so now we have the subsurface. The subsurface is full of these bubbles, and now we ask ourselves, how does, right, a domain like this one made of, for example, water and gas deform as a seismic wave hits it, right? What happens? Well, we have three different parts, and we have a first part, which is the elasticity of the water, which is simply, the Hooke's law. We can assume the water to be perfectly elastic. So, fundamentally, the deformation is a function of the bulk modulus of the water, or the liquid in general. But then we have the bubble, and the bubble itself do have also a certain bulk modulus, which is the bulk modulus of the gas. But as the pressure in this container changes, we are going to move moles of gas in and out of this boundary, and that is going to take energy from our seismic waves, and it's going to introduce attenuation. And I've been studying this since 2015, and lately we had some new work done. So the idea is this one, right? You have a wave that fundamentally changes the volume of this, and this is the bubble. As the wave gets positive, the bubble gets smaller. Part of the gas gets out and dissolves in the water. When the wave instead is negative, meaning the force is lower than the initial force, then the bubble eventually expands, and then you have gas falling inside the bubble. Now, the first thing we want to do is to take the widget model, which is wave-induced gastric solution dissolution model that we developed in 2015, and we want to find what is called the relaxed and unrelaxed limits. So what happened when I take my container, which has inside liquid and a bubble, right, and I squeeze it very slowly, right? What happens? That's the relaxed limit, okay? And what happens instead when I try to squeeze it extremely fast, right? I can't do it, you know, extremely fast. So that is fairly simple because this unrelaxed and relaxed limit, which gives you how stiff is the container of liquid with the bubble inside, is fairly simple to calculate. And it comes down to be a very simple equation where 1 over the bulk modulus is nothing more than the isostress relation, or Royce, right, bulk modulus, which is of course a function of the bulk modulus of the gas, how stiff is the gas itself, the saturation, which means how much gas into respect water there is, and then the bulk modulus of the water. But then there is this instead, this part here, which gives you instead the low, the relaxed limit, right? This low limit here, which is all related to the fact that the bubble eventually is going to dissolve inside the water, okay? So this gives us the equation for the relaxed and the unrelaxed limit. And then here I have to be very careful because the chair of mathematics is present. And this is me with mathematics. Can you believe the hula hoop has fallen after a millisecond after my wife has taken this picture? I believe you know, I think you can believe that, right? Yeah. A lot of effort, right? A lot of effort. And now we want to find an analytical solution for this, right? Because we did have a numerical model. A numerical model was working, it was kind of fitting the data, but I was not very satisfied. Also because a very nice reviewer from NSF told me you should find an analytical solution before doing numerical experiments, right? You know, those picking, comments, right, from NSF. Anyway, the point is I want to find an analytical solution, and the idea is that the volume of my bubble, right, it must be related to the very famous equation PV equal nRT, right? It's easy, right? The volume, the dimension of that bubble in there must be related to that. The problem is that the number of moles that is inside the bubble, right, changes because as the wave goes through, it's changing the pressure, and I do have gas getting dissolved and exsolved in and out of the liquid. So this becomes a fairly complicated problem. And it has to do for sure with the Fick's law, because as I dissolve or exsolve gas in and out of this boundary, I need to consider that the concentration of the gas is going to change in the liquid, right? So I need to find a solution for that. So this equation suddenly becomes extremely complicated. Okay, here I am assuming I'm imposing a sinusoidal wave, right, at the boundary here. The pressure is fundamentally the same except for the surface tension that is accounted for. And the other thing I'm considering here is that the temperature is considered constant. And that's it's really a simplification which might lead to some errors, especially when the pressure variation is extremely high, right? But the pressure variation, right, here, the P0 has to be much smaller than the initial P, okay? The pressure at which the gas is. Okay, so the equation is this one. It does not have a trivial solution. It's a series, and it involves a spherical Bessel function, which I don't even know what they are. No, I'm kidding. I know what they are, but I don't want to deal with it. But if you want to find a simple high frequency solution, which means the limit, what happens around that limit I was explaining before, right, when you squeeze this very quickly, you can take a simplification of that, It's called Jacobi angular expansion or plane wave expression, and you can use this as a good solution for this PD. Now, the other thing you need to think about is that the concentration of the bubble liquid interface, like the rest of the liquid, right, should follow the Henry's law, which tells me how much gas can I dissolve in the liquid given a certain temperature and pressure. Okay. Now, you take the derivative in time of those, and you fundamentally equate those two equations, and you end up with this solution here. Okay. Now, the other thing you have to say, this is the concentration of my gas inside my water, okay? From R equal R to RE. RE is the size of the gas plus liquid, and R, big R, is only the gas, okay? Now, the other thing you need to do, you have to think about the gas quantity rate between exchange rate. There's an exchange missing there. Between the bubble and the liquid, it must be the integral, right? Of the flux itself, right? And so you take that one, and you end up with this equation. And this equation gives you the number of moles as a function of fundamentally pressure, okay? And now you can plug this n inside this equation, and then you can calculate how the volume of the bubble changes as you are changing that pressure outside. I'm sure the chair of mathematics has already found an error. And then you have to add, of course, the deformation of the water, which is elastic, so that's trivial, okay? Now the question is, how can we verify this? And I was very lucky to have a couple of students. One is Zichi Jin, who was a visiting PhD student here in 2019-2020, and now I have Isabel Lambert has been working on this problem, and they put together a very interesting, I love this experiment because it's simple. So we have a simple Arduino board which controls a stepper motor, and the stepper motor pushes on this syringe, which is a high pressure syringe, and there is a bubble in there which is under this microscope. And we do measure pressure because there is a pressure sensor here, okay? So we look at the deformation of the bubble, and at the same time we look at the pressure. Okay, so the force applied here, that's my bubble, right? And then I'm going to look how the bubble deforms. And this is what we do. We look at the bubble, we give a step of stress, and then the bubbles start deforming. And very interestingly, we increase the pressure, we keep the pressure fairly constant. That vibration I will tell you later if you're interested to know what it is, but this pressure is fairly constant, while the dimension of the bubble keeps going down. And that is because my bubble is losing gas due to the fact that the gas is dissolving, right, in the water, and is going far from the bubble itself, right? Now I take my data, the pressure and the radius of the bubble, I calculate the volumetric strain, right? And the volumetric strain can be fit with a very simple phenomenological model, the standard linear solid, which is defined, strain, right, is defined by this equation, and this gives me a solution for the bulk modulus of the bubble and the attenuation of the bubble. So fundamentally, when I stress my bubble very slowly, my bubble is very compliant. You can see here, this K value is extremely low. But as you go up with frequency, and I get, for example, 1 Hertz, my bubble becomes extremely compliant, extremely non-compliant, extremely stiff. Because the gas does not have time to leave the bubble, diffuse inside the liquid, and eventually let the bubble shrinking, right? You're kind of locked, right? Those moles of gas are continuously going in and out of the bubble, so the bubble eventually becomes like sealed, right? And then you get to the limit where your bulk modulus is simply the elastic properties of the bubble and the liquid, and there is no dissolution anymore, okay? Now, how does these two results compare? They compare fairly well. Okay, this is the high-frequency short-time analytical solution. A lot of effort during the last summer, and this is the result from the experiment. And of course, they don't match really well here because that is a high frequency analytical solution, right? So now I can take these results, I can take these values, which are again, how stiff is my water plus bubble? Very compliant, very stiff, depending if I'm stressing this very slowly or if I'm stressing very fast, which is the frequency of my seismic wave. And now I can take the properties of CO2 and hydrogen, for example. I can take the properties of CO2, and I can show you, for example, that for CO2, this change in stiffness happens around, for example, 100 Hertz for a bubble which is 6 micrometer size in a pore which is 6 micrometer size in diameter, and a pore which is 42 micrometers diameter. Here we are talking about a pressure of 10 megapascals, so roughly a kilometer, whatever, in the subsurface, right? For hydrogen instead, that frequency corner is also called frequency corner, where this change in compliance happens. It's a much lower frequency. And now this allows us to make a prediction of what happens when that liquid is inside a rock. If we take that liquid, right, the property of those two liquids, and we mix it with the property of the rock, we get the property of a saturated rock with that liquid. And this is what happens. It happens that a rock, like a brass sandstone saturated with hydrogen, will show a velocity increase but from 3,500 to 3,600 meters per second, and this increase happens pretty much around 1 Hertz. At the same time, the same rock but saturated with CO2 will have a much higher increase in velocity from 3,400 to 3,600, and that happens around, whatever is that, 20 Hertz, right? And these are the attenuation curves. And for example, we can have a quality factor of 25, which is a fairly low quality factor, fairly high attenuation, 0.04. 1 over Q is attenuation, Q is quality factor, okay? So at 4 Hertz, we can have a quality factor of 25. So now, what we can do with this, right? We can take this, we can bring it to the real geophysicist who does simulation of propagation in the subsurface. We can create a couple of models. These are toy models, of course. We can say, okay, now we have a reservoir, everything is elastic, we propagate a wave from here, we record the wave here, right? And we want to look how those waves which are recorded here change as we introduce a quality factor of 25 in the reservoir. And this gives us, a fairly big change. If you look here, there is a very noticeable change, right? So this is what we do with bubbles. And let me see how much time I have still. Oh, that's good. 31. How many hours do I have still? Okay. Part 2. Part 2 talks about CO2 sequestration, carbon mineralization, and how the injection of CO2 in the subsurface can be used to kind of save ourselves from the climate crisis, maybe. Sequester a bit of CO2 in the subsurface by creating carbonates. The injection of CO2 in certain rocks, like basalts or ultramafic rocks, generate carbonates, and those carbonates lock that CO2 in a solid form. So that is a very safe way to store or to sequester our CO2 in the subsurface. I want to say that this is preliminary results, and this is a recent paper in US about exactly this. The idea is that you will have your factory that generates CO2, and instead to release the CO2 in the atmosphere, you're going to inject in the subsurface. As you inject in the mafic, ultramafic rocks, inside fracture, you will start forming these minerals in some of the fractures. And eventually, those fractures will extend because the formation of carbonate in the subsurface increases the volume and of the minerals that the CO2 reacts with, and that eventually will extend the amount of CO2 that you can store in the subsurface. These are examples from Oman, very famous. of veins, or natural veins of carbonate inside those kind of rocks. And this is an example of carbonate formed in basalt from the Carbfix site in Iceland. Okay, I was very lucky again to have two amazing scientists. One is a master student, Saleh, and the other one is Dr. Clay Wood, who's a postdoc, and they've been working on this for a couple of years. This is a ARPA project. The PI is ST Uker, a BG. And the idea is that we inject our CO2 with our water, and we don't really know what happens to the subsurface, right? So we want to understand through laboratory experiment what is going to happen there, right? Sorry. So one of the very famous, one of the most simple reaction that eventually happen is that if you have olivine down there, you're going to create carbonates, and that is what we're kind of aiming to do in our laboratory. This is a famous paper from Adam 2013 when they did this kind of experiment in basalt, and they see the formation of carbonates around these minerals. Now the question, one of the big questions is, when you will start injecting this CO2 in the subsurface, you don't really know where this change between the dissolution of silicates and precipitation of carbonates happen. You inject your fluid, and you don't know if the precipitation of carbonates is going to happen just outside the well, or is it happening a kilometer away, 10 meters away, 100 meters away. Eventually, by tuning the injection rate, right, we might be able to use pretty much all the subsurface, right? Or, for example, we could use two wells, right? One well is in the injector for a while, the other one is the producer, right? And then you invert them in order to use all the subsurface to precipitate everywhere your carbonate. So, because we don't know very well what controls the kinetic of these reactions, we don't really know, where this is happening. And again, seismic monitoring, the fact that we can use seismic methods to understand what is going on, might help, right? Okay, so here we are using serpentinized dunite. This is a sample that Saleh used. We crack it. We made a fracture in between because there's very low permeability rocks. It's almost impossible to inject fluids if you don't do something like that. The typical porosity between 2 and 4%. That's the density. They have a lot of serpentine. So they are serpentinized dunites. So all the olivine has been already, a lot, has been already transformed in serpentine. There is still a bit of olivine, and there is a bit of brucite, which also is a phase that can react and form carbonates. And we built a couple of instruments, which I like also, but these are more complicated than the instrument I showed you before. This is a reactor which can go at 300 Celsius and up to 50 megapascal, so 3-4 kilometers depth. And we can inject our fluid inside a sample which is under this jacket by controlling the fluid that has been injected by this pump and mixed before in this cylinder. The idea is that what we can do while we are injecting that water with CO2, that fizzy water, we can listen to the acoustic emission, which is really the sample screaming while we are torturing it, right? And we can measure the PVS, the velocities, how quickly those waves travel. And we can measure the permeability. How does the permeability changes? Are we clogging that fracture, right? Are we closing? Are we opening? What is going on, right? Okay, so these are the results. So before and after, you can see that the rock has clearly reacted. We found the presence of nestionite, which is a carbonate, but is hydrated, and also chrysotil, which we are not going to say the commercial name of chrysotil. Okay, right. So the injection started in August and it ended in January. So the big thing of this machine is that allows you to do this experiment for months. And that's what we need to do because experiment like Carbfix, for example, is going on since 20 years, 15 years? Yeah, 15 years, right? And these reactions, they are probably extremely slow. So we need apparatus that can keep the sample at constant pressure and temperature and injecting those fluids for a very long time in order to understand what is going on. And what we see here, we see that the velocities that travels through the sample increase pretty rapidly and then stay steady. I'm looking at the black curve. The energy of those waves, the amplitude of those waves, also increases fairly rapidly and stays together. At the same time, the acoustic emission, which are this cracking generated by the fact that we are creating carbonates in some of those small cracks, right, ramp up pretty rapidly and they stay kind of flat except in here. So we start the injection here. This was not a fractured rock. We used a non-fractured rock on purpose to see how difficult it is to inject fluids in there. And it was extremely difficult. We injected 20 milliliters of water and carbonated water in roughly a month and a half, right? So it took a long, long time, okay? And then here eventually, we injected other 20 milliliters of water, and then suddenly, the permeability, which is these blue dots here, I chose blue and black on purpose, right? Because those are the best color ever. Okay? So the permeability goes up, it goes roughly at 6 micro-C, and then eventually here we have done other things, we have hold the fluid in there, and then eventually we have injected, we have started slashing that fluid back and forth in the sample, so we never change the fluid, in order to increase the pH and allow to precipitate minerals. And what happens is that the permeability from high, it goes down and then it stays down. We still have to understand why every time we are inverting from upflow, so we are injecting the fluid from the bottom to the top of the sample, and then we invert, we inject from the top to the bottom of the sample, right? The permeability goes up and then start going down and so on and so forth. This is something we need to understand, okay? It's probably due to the fact that we are remobilizing some of the precipitates and so on, okay? Here we see also that the velocities decreases a bit and the energy decreases a bit. This could be the evidence that our porosity is changing because the waves, how fast the waves go is inversely proportional with density. So if you have a less dense material, the velocity is going up. If you have a more dense material, the velocity is going down. So this small decrease in velocity might be related to the fact that we are precipitating minerals in the rock. So the rock is becoming denser. And these are CT scans of our samples. Now we can scan the sample before and after, not during. And this is the pore space. The white part here is the pore space. And of course, this is the sample, just a cylinder, just to show you where the sample is. And the sample had a couple of natural fractures that they were not open. And what is very interesting is that the pre and the post is clear that there is more white, so we have dissolved part of the rock, right? But the interesting part is that we can clearly see with the CT scan that we have opened up a series of pores in between this fracture here, which was probably the place where the fluid was flowing into here. So the water wants to escape to the other side of the sample. So we are injecting from the bottom, the water and gas enters here, and then you want to find a way to escape, and you probably find this way to escape here. You can see it very well here, this cloud of dots, which are probably new porosity formed due to the dissolution of the rock. So with the CT scan, right, we can see that. And the CT scan also allows us to see how much the porosity increased, which is here roughly 0.15, which is half of what we have been measuring with other methods. But still, the CT scan can really provide us important information on what is going on in the rock. Now, the CT scan is important, but with that machine we can do CT scan only at the beginning and at the end. We can't do CT scan while we are injecting the fluid, right? Therefore, we have here Saleh, who is a master student, is working very hard in there, right, inside the CT scan of UTCT, and is mounting his machine inside the CT scanner to look inside the rock while we are injecting the fluid. And this is the machine, the sample is inside here, it's roughly 12 millimeters diameter. Of course, it's jacketed, you are confining the sample, right? So you want a stress around the sample which is higher than the pore pressure in order to be able to inject those fluids. And I have to say, he built all this like Clay did, like Clay built the other machine. And the idea again is that you have a chamber where you mix that water and CO2, and then from there you inject it inside the sample, and then you withdraw it inside a syringe pump. And the beauty of this is that you can do scans throughout the entire experiment. And this is the sample before, so we fracture it, and this is the sample after, and you can clearly see that the sample has reacted with that water and CO2. He has created chrysotile probably, and we also found esconite in this sample as well. These are some scans taken at different times, roughly 14 days after the beginning of the injection and 26 days after the beginning of the injection, and you clearly see that in some places you are dissolving that rock. You are dissolving that rock, and then if you go further in time, at a certain point, in those fractures which are around the main fracture, exactly like this paper was depicting, you can see that some precipitates start to happen. So with a CT scan, we can depict those things. We can really see where the precipitation is happening. And these are the 6 scans that Saleh has taken from the 24th of September to the 15th of January. We did have a hiccup here with the CT scan. It was down for a while. So what we did, yeah, Rich is like, yeah, it happens. What we can with that, right, we can look at the porosity, how the porosity evolved throughout this time. And the very interesting thing is that you have an increase in porosity and then eventually a decrease in porosity from the CT scan. At the same time, this machine can also measure permeability of the rock. So this arrow here indicates where we are injecting new fluid. So fresh fluid has been injected in the system. And you can see that every time we inject new fluid, the permeability spikes up against black. Okay? And